Mr. Hevel, you have a calorimetry experiment for us today?
We do, Mr. Moore. We have calorimetry galore here. Absolutely. So, what we're doing here is coffee cup calorimetry and everybody's favorite, Hess's law. And here's what we're trying to accomplish. We're trying to determine the enthalpy of formation for solid magnesium oxide. That's your goal. So, there's actually 3 different reactions that you're going to combine using Hess's law to calculate that enthalpy of formation for MgO. And it's important to remember how this is defined. Enthalpy of formation has a very specific definition. So you have to think about that definition when you're trying to come up with this equation.
So yes, notice we're not giving you what the chemical equation, the target equation for our Hess's law solution. You've got to come up with it.
Right. Okay, but think about the definition, and you can see what that equation is going to be. You're trying to find the change in enthalpy for this process.
Okay.
Now to do that, we're going to run 2 different chemical reactions experimentally using coffee cup calorimetry. And then you'll have to add in a 3rd equation that is the formation of liquid water. Now this one isn't experimental. You're just going to basically look that up. Okay? So here are our 2 reactions. Here's what we're mixing together. One reaction is solid magnesium metal with hydrochloric acid. It's going to react and make magnesium chloride and hydrogen gas. Our other reaction is solid magnesium oxide, again reacting with HCl, again makes MgCl2, but water in that case. Okay? Now you're going to have to figure out the net ionic equation. We gave you the molecular equation. You'll need the net ionic. Okay? And, hopefully you can read my blue writing down here, you're going to pick one of these reactions to be the basis of your particulate drawing. Okay, just one of these for your particulate drawing, whichever one you like the best.
Okay.
Okay?
So yep, we have these 2 chemical equations. Those are experimental ones. This one, you have to write the equation, come up with a delta H just from the table.
Right. So
Those are your 3 given equations. Yep.
Coffee cup calorimetry process will get you the delta H value for these 2. Okay? Now in the end, what you're going to do is figure out what's your percent error between the experimental value and the theoretical value for the enthalpy of formation of magnesium oxide. So over here, I don't know if you've dealt with percent error before. Percent error is the absolute value of your theoretical value minus experimental value over the theoretical value times 100.
You probably have used that before, but we wanted to just make sure you have it.
Exactly. Okay, and realize that you can look up the theoretical value for the enthalpy of formation of MgO.
Well, it looks like we're set up for an experiment.
We are. Mr. Moore, coffee cup calorimetry on a Friday afternoon. That's awesome.
Yep.
So, coffee cup calorimetry, of course, means using coffee cups. And in Troy, we believe in using nothing but the finest for our students. So we're using not just 1, but 2 styrofoam cups nested together.
It's very nice equipment.
It is. It is. And this is our precision high-tech lid.
Wow.
That we're also going to use. You just don't find these anywhere.
No, it looks like it was made in America.
It was, for sure. But it is important. With coffee cup calorimetry, you're assuming that all the heat flow is occurring inside the cup. And we have insulated the inside of the cup from the rest of the surroundings. There's nothing out here that's going to influence the heat flow in there. It is important.
Yeah, styrofoam is cheap, but it works really well.
It's really good. So, the first reaction you recall is between hydrochloric acid and magnesium metal. And so we're measuring out our HCl. I'm going to set it down so Mr. Moore can focus better. It's rotated properly.
Okay, that's good. Let's see if I can get that. Now, we do need to take note of what the graduations are. Boy, I had that sink right in the background too. But yeah, you can see the 40 down there and then the 50. So it's graduated to the whole ml. And he's got the meniscus right on the 50. So how do we read that volume? What would you say the volume is if it's graduated to the whole ml? There it is. And what about the concentration of the acid?
Oh yes, Mr. Moore, almost forgot. So this is the acid we're using. Now, I wrote just 1 molar here, but it's really, think of it as 1.00 molarity HCl that we're using.
Yep.
And we'll need a thermometer to measure our temperature. And so, here's the thermometer we're using. I'll point out this is Mr. Moore's favorite thermometer because it has blue spirit in it.
We had a dozen of these at one time, and now we are down to 1.
Yes.
I just want to cry when these things got broken over the years, but yeah, so we take very good care of this one.
Yes, we do. I don't
So
know if-
yeah, take a look at what the graduations are now. Looks like it's graduated to the whole degree.
Right.
Just so we know how to read that, how many
Yeah.
sig figs to use.
Sig figs are important. Okay, so I'll dump the acid into our calorimeter. We'll need that initial temperature. So let's see if we can get the thermometer to stand up. Doesn't always want to. Well, it's not going to stand up.
We have seen so many setups like this that have been bumped and fallen over. In fact, we did one of ourselves in an earlier trial. Come on. Okay, there. We've had the same initial temperature every time. Isn't that something, Mr.
That is
Hill?
amazing. Pretty steady. All right, so that's ready to go. Now, we need the magnesium. So here we go. We have a piece of magnesium ribbon. And you'll want to know the mass of that.
There it is.
Okay. And now, we're going to add it to the acid and see if we can measure the temperature change. So it doesn't waste any time. It starts up right away. And I don't know if you can hear the fizzing.
Yeah, we can see something in there. Oh, yep. Yeah, you see that. Oh. And that is hydrogen gas going right up Mr. Helvel's nose.
Which is unpleasant.
Hydrogen is nasty to breathe. It will burn. It gets your nose. It'll make your eyes water. It hurts. It'll make you cough.
Yep.
We have cleared the room before with hydrogen. Mr. Helvel's doing some gentle stirring in there just to keep that heat distributed evenly throughout the water. You can't, if you don't stir it, you can't actually get hot spots in there. The bottom might be warmer, the top might be warmer, and you want it to be consistently distributed all the way through.
Okay, I don't know if the temperature's done changing. I think it's all dissolved.
Oh, looks like we've had quite a change in. Ooh, if you could just turn it back toward you. Can you hang on to it? Just give it a roll. Okay, right there is good. We can see that. There's our final temperature for this trial. We're gonna try to hold it still. Can you see those whole numbers? Okay.
Okay, reaction number 1. Okay, same deal.
So we're going to trust Mr. Hevel with this one. He'll measure out 50 ml and just dump it right into the calorimeter. I feel a little bit sorry for him not being able to see so well, knowing that will be me in a short amount of time.
It's pretty good. Okay, here's your 50 mils HCl. Now, so far today, the temperature, the initial temperature has been exactly the same every hour. So.
That's not focusing very well. We get flashes.
You want me to stand it up?
Oh, we can see that well enough. Actually, it's a couple of tenths higher than it was the first time.
Oh, was it?
Yeah.
Okay. Okay, now here is the magnesium oxide. It's a white powder. It's almost like
Okay.
flour.
All I have is clear. There. Okay, yeah,
It's
that's good.
very fine.
Yep. Oh, I don't know that you had that zeroed out.
I hit.
Yeah.
I hit the zero. No?
Was it zeroed? Okay.
Well, no, that's too big of a mass. Hold on. I swear it was 0. All right, let's try again. Definitely reading 0 now.
Okay. Massive MgO.
Okay. So here we go. Dump it in. See what happens.
This reaction is not as dramatic. Everything stays in. There's no gas that's emitted or anything. It's just all aqueous.
It's a little cloudy in there.
Oh, come on. Oh, there we go. Final temperature.
Good deal. Now, one final thing, because it's confusing every year doing this lab. You have to use the Q equals MC delta T equation to calculate heat. And so you need to plug in a mass. We realize that the HCl solution we're using is almost entirely water. There's a little bit of HCl, but it's almost all water. So pretend it was 50 milliliters of water and convert that into grams. Use that as the mass in
Q equals MC delta T equation.
Good reminder. So we're now going to try to find the experimental heat of formation of magnesium oxide. Good luck.
Good luck.